The next fluid properties that we will look at is surface tensions. So generally a liquid will form an interface with a second liquid or gas. And if you consider the molecules in this fluid and compare the forces which is acting on the molecules within the fluids and for the area close to the surface. So molecules near the surface have greater attraction with each other because of the unbalance in forces. So if you consider a liquid, this is the surface of the liquid, and we consider the molecule inside the liquid. It has molecules connecting to it in all directions. So the forces are actually balanced. If you consider molecule right at the surface of the liquid, it has forces at the bottom and at the side, but there's no molecules on the other side. So there is unbalance in forces, and because of that, it gives rise to surface tensions, which actually will try to reduce the area of the surface as much as possible. So the unbalance in forces cause surface of the liquid to be in tension. It gives rise to certain phenomena. For example, we can see that water bug can actually sit on top of water without sinking. So surface tension sigma is measured as the force acting across a unit length of line drawn on the surface of the liquid, and it acts in the plane of the surface and normal to any line on the surface. So if I have any surface of liquid, so I draw a line, let's say of length L, so there will be surface tensions. And the value of the surface tension force is equal to sigma multiplied by the line. And it is actually acting on the same plane of the surface and perpendicular to the line. So it is actually force per unit length, right? So if you consider the dimension, so force is ma over length. So it's actually mass L t minus 2, that's for accelerations, and then L minus 1. So the dimensions of sigma is actually equal to m t minus 2. Right? And then of course the unit is Newton per meter. There are quite a few effects of surface tensions. So you will try to reduce the surface of the liquid to a minimum, right? So that's why you can see that droplet will tend to be spherical. And then if you have a droplet or a bubble, the pressure inside the bubble or inside the droplet is actually higher than the surrounding pressure. And another effect is actually capillary effect. Surface tensions is a function of temperature, and generally it is actually related to the intermolecular forces. And because of that, generally surface tensions reduces with temperature. So let's consider a droplet. That's a droplet, right? So it's a spherical shape. So if you consider the pressure inside the droplet and outside, so let's say this is P inside, this is P outside, because of the surface tension, Pi is actually bigger than Po, and there is actually a delta P, and this is actually called excess pressure. So let's consider the value of this excess pressure. So in order to do that, if I just cut the droplet into half and draw kind of like free body diagram. So I cut the droplet into half. So the pressure outside is actually equal to P out. So let's say it's acting like that, okay? And then the pressure inside is actually equal to Pi, is acting like that. And then on the surfaces which has been cut, there will be surface tension forces. So on this line, along this line, so that is surface tension force, and the value is actually equal to sigma multiplied by 2 pi r, where r is actually the radius. So I can balance this force, let's say in the vertical directions. So I have pi minus po multiplied by the area, which is pi r squared, this area here, and that must be balanced by the surface tension force, which is sigma 2 pi r. So this is the excess pressure. So delta P is actually equal to sigma 2 pi r divided by pi squared. So delta P, the excess pressure, is equal to 2 sigma divided by r. We can do the same analysis for a bubble. So the difference between a bubble and a droplet is that inside the bubble there is actually a gas, right? So if you think about it, two lines has been cut. I think the actual thickness has been exaggerated. So this is, I call this one Ri, and this is R. So two lines has been cut. If you consider the forces again, so outside, here are P out. If I consider vertically, so P out A, and then this is P in A, and then the surface tension force will be on the outside part and also on the inside surface which has been cut. I can balance the forces again, so I have Pi minus Po multiplied by pi r squared again, okay, and that must be balanced by surface tensions 2 pi r I plus 2 pi r out. But Ri is almost the same as Rr, so let's call that one that's R. So I have, this is the excess pressure, pi r squared, and that's equal to 4 pi r, so this one is to multiply by sigma. So I have delta P is actually equal to 4 sigma over r. So if you compare just now for droplet, delta P is actually equal to 2 sigma over r. For bubble, delta P is equal to 4 sigma over r. So it's 2 times higher. So we can do the same analysis for a water jet. So let's say we have a water jet. So water jets, let's say it's like that, right? Okay, so let's say the length of the water jet is L, and then the radius is against 2r. So again, we divide it into half and consider the forces acting on it. So again, we can easily write the net forces due to excess pressure, that's equal to delta P multiplied by 2r multiplied by L, and then the surface tension force is here. So on this side is sigma L, so on this side also is sigma L. So we just ignore these end parts. So basically we have delta P multiplied by 2RL, and that must be equal to 2 sigma L. So we have delta P is actually equal to sigma L over 2RL. So delta P is actually equal to sigma over R. So that's excess pressure for jet. Surface tension gives rise to an effect which is called capillary effect, which is shown in this diagram here. So basically, if we have a tube and the tube is actually immersed in a liquid, what will happen is that part of the liquid will try to raise within the tube to a certain height, delta H as given here, right? So what happened here is that the surface tensions will actually cause it to to raise upward because of the imbalance in forces. So there is a net force trying to pull it upward due to surface tension, and this is actually balanced by the mass of the fluids downward here. So we can actually calculate this height h here if we balance the force in the vertical directions. So if we consider the capillary effects for a liquid which actually adhere to the surface of the tube. So if we consider the tube, so this is the tube and this is the liquid. Part of the liquid will raise upward like this. And let's say form an angle theta. If you consider the surface tensions, so the end parts of the liquid is actually being cut like that at an angle theta. So this is also theta. So the force here, which is pulling it in the direction of theta, is equal to sigma by d, where d is actually the diameter of the tube. So the height at which it goes up, call that one equal to delta H. So if you consider the forces which is acting here downward is equal to mg, where m is actually the mass of the fluid which has gone up. And then this will be balanced by the vertical components of the surface tension force. So we can balance the force. So what we have is actually mg, which is acting downward, is equal to sigma by d. But that one is actually at an angle of theta, so we have to take cos theta. But if theta is actually very small, so almost 0, so that means that we have cos theta is about 1, right? So we can rewrite it again. So m is actually, we can calculate that's rho multiplied by volume. So volume is actually pi d squared over 4, which gives us the area multiplied by delta H. Then multiplied by G, and that must be equal to sigma by D. So from there, we can rearrange for H. So basically, this pi cancel, this D, one of the D cancel. So we get the expression for the height at which the liquid will go up, which is actually equal to 4 sigma divided by rho g d. So we can see that if sigma is high, so the height will be higher. If the diameter is high, so the height will be lower. If the gravity is high, then it will reduce delta H, and if the density is high, so it will reduce delta H. So just now we have looked at the case whereby the liquid adhere to the surface of the tube. So now let's look at the case if it doesn't adhere to the surface of the tube. So here let's draw the case again. So let's say like that's a tube. So what will happen is that the surface of the liquid inside the tube will be kind of like depressed. Let's say like that. So if we put a tube, for example, in mercury, this is what will happen. Well, let's write. Let's draw all the values. That's delta H, right? This is the diameter D, right? And this one is actually, let's say, at an angle of theta. So again, if you consider the surface tension force there, equal to sigma by d, right? That's in this directions. So now, although the gravity is actually pulling it downward, what happened here is that because of the fact that the mass of the fluid here has been depressed, so that means that equivalent mass outside has been pushed up, right? So we can also write the equivalent force upward, which is actually equal to mg, and this must be balanced by the surface tension force here. So we can again balance the force in vertical direction again, we can write same equation. mg is actually equal to sigma pi t cos theta. Normally, theta will be quite finite. It's not 0, so we cannot ignore the value. So this is density multiplied by pi d squared over 4. Okay, multiplied by delta H multiplied by G, and is equal to sigma pi d cos theta. Right. So again, we have the same formula, but we have to put cos there. So for sigma cos theta divided by rho G d. Now let's look at this case. So basically similar to the one that we did earlier, but this is with numerical values. So here we have mercury. So mercury doesn't adhere to the surface of the glass. So when a glass tube is immersed in a pool of mercury, the meniscus is depressed, right? So the surface tensions of mercury is equal to 0.514 Newton per meter, right? So find the depression distance in a 1 millimeter glass tube. Okay, let's draw a schematic diagram. So we have a glass tube. So it's immersed in mercury. And what will happen is that it will be depressed like that. And then it will make an angle theta, right? Okay, and we asked to find the kind of like the average d, and the diameter is given as I call it big D, is equal to 1 millimeter, and the fluids that we are dealing here is mercury, whereby we know that sigma for mercury is equal to 0.514 Newton per meter. So you ask to find D. So again, if we consider the forces acting on this, so the force acting downward is actually equivalent to mg. So mg is basically equal to rho multiplied by the volume of this. So it's pi d squared over 4, right? And then multiply by d, then multiply by g. And then the force which is acting here, which is equal to sigma pi d. So the force which is acting downward, the component acting downward is actually sigma pi d cos theta, right? So now we can balance the force in the vertical directions. So we can write sigma pi d cos theta, and is equal to rho pi d squared over 4 dg, right? So we have expression for d is just equal to 4 sigma cos theta divided by rho g d. So all we need to do now just put the numerical value. So for sigma is given as 0.514, and then cos theta, so that's 40 degree, okay, divided by density of mercury is 13,000. It's not given, but we know that it's 13,000. Gravity is 9.81, and then the diameter is 1 millimeter, so 1 times 10 to minus 3, right? So that gives you d is equal to 0.0123 meter, or is 12.3 millimeter. Okay, the next problems that we'll look at is concerning a water bug. So the question says that a water bug is suspended on the surface of a pond by surface tensions, meaning that it doesn't sink, right? So it means that water doesn't wet the legs of the bug. So the bug has 6 legs altogether, and each leg is in contact with the water over a length of 5 millimeter. So you are asked to find what is the maximum mass in gram of the bug if it is to avoid sinking. Okay, so let's consider these problems here. So let's draw a schematic diagram. So we have this water bug, and then it has 6 legs. Let's consider just the legs which are in contact with the water. So given that the leg which is in contact with the water is over the line, I call that small l, that's equal to 5 millimeter. And then it has 6 legs, and if I assume, because temperature is not given, so I assume that it's equal at 20 degrees C. So if I use the table, the surface tensions table, so sigma is approximately equal to 0.73 Newton per meter. So now we are asked to find the maximum mass. So let's consider what actually happened to the leg, right? So let's consider the leg like that. When the mass is small, only these portions of the leg will be kind of like in contact with the surface of the water. So you can see that it will cut the water surface there. So that will be the surface tensions. And then the vertical component is actually, if I call this one F surface tensions, so that is, if I call this angle theta, so the vertical component is actually equal to Fs sine theta. But as we increase the weight, so what will happen is that the value of theta will be bigger. So when the value of theta will be bigger, the surface tension force also will be bigger because theta is bigger. Theta is highest at theta equal to 90 degrees. So that means that at the maximum mass, what will happen is that half, so it will be in that position, right? So meaning that the surface tensions will be exactly upward like that. And then each leg will actually cut 2 different lines on the surface of the water. So if you consider the leg like that, right? So it will cut here and it will cut here. So it will generate surface tensions here, which is equal to sigma L. And then here also is equal to sigma L. So each leg will have 2 sigma L. So that means that it has 6 legs. So total surface tension force upward will be equal to 2 sigma L multiplied by 6, so 12 sigma L. If you consider the part again, so the surface tension force upward will be equal to 12 sigma L, and the weight downward will be equal to mg. So we can balance the force. So we have mg is equal to 12 sigma L. So we can get m, which is equal to 12 sigma L divided by g. So that's 12 sigma is actually 0.073. Length is actually 5 times 10 minus 3 divided by 9.81. So that gives me 0.45 gram. So that means that the maximum weight of the bug is 0.45 gram. Bigger than that, it will sink. Now let us watch a video related to surface tensions.
This one's fun. Make a little boat out of a card and then place the boat on the surface of the water. Now use your soap to break the surface tension and power the boat. Take an open jar full of water and put a card over the top. Flip it over and it'll hold up the card. Now this is a pretty well-known trick, but what about this one? The water stays in the jar. Oh yeah, I forgot to mention that there's a screen on the top of this one. I switched them. Tricked ya! I screwed the top of the jar over the screen so that it's on there really tight. Now when you turn the jar over, you can slide the card out, and the surface tension across the screen is enough to hold the entire jar of water up. But it's still open. I can stick some needles into the screen And the surface tension still holds the water. I love this one. Take a paper clip or a pen spring and balance it gently on the surface of the water. And if it doesn't work, you can always try with tissue paper. Oh, see, there we go. Place a bit of tissue paper on the surface of the water and move the tissue paper out from under the paper clip. Okay, I'm gonna take a little bit of soap on the end of a Q-tip, and if I touch the water with the end that doesn't have soap, nothing happens to the paper clip. But I'm gonna touch the surface with the soap and watch what happens. It immediately falls. Kinda surprising. This one's pretty easy. See how many drops of water you can fit on a penny. The number may surprise you.
So let's see how surface tension prevents water from pouring off from the jar. We have the jar. And then at the end, there was a screen. So what happened was that if you consider every single parts of the screen, so let's say that's the screen, it's actually cut the surfaces by a length L, right? So if you consider all this length here, so sigma L multiplied by the surface tension value, it's actually balance the weight of the water. So if you consider this is the jar of water and the screen at the bottom here, so the weight here is equal to mg, and it's balanced by the surface tension forces here. So you can write sigma L, where L is each one of these here, and then summations of all the parts of the screen, and that must be equal to mg.